Hey, let's do some physics. Pull out 1998 B1 and give that a read. Go ahead and pause the video. And now that you've had a chance to do that, you should have noticed, I hope, that this is a pretty familiar type of problem to you. It should look a lot like our Newton's second law lab number 1 and number 2. Instead of a cart moving along a track, you've got block A moving across a table, but other than that, it is pretty much the same. If you look at letter A, it says determine the acceleration of block A as it descends. That's a typo. That should be block B. Block B is descending, at least at the beginning here. So, calculating the acceleration of block B. Well, you've got a couple ways you could do this. Right, we looked at a long way and an easier way. The long way is a little bit messier. That's where you treat block A as its own system, block B as its own system, and then you've got external forces on those systems and the tension. Right, the tension of the rope would be outside the system, and you'd need to include that in your Newton's second law equation. That's a mess. We don't want to do that. So let's treat this as one big system. Right, and the reason we do that is that way the tension in between the blocks is an internal force, and we get to ignore that and when we look at Newton's second law. So let's say our system is defined as block A and block B and the string between them. Alright, so the quick way to do this then is to say that the sum of all the forces acting on the system is equal to the mass of the system times your acceleration, right? That's Newton's second law. Sum net force equals EMA. There's really only one external force acting on the system. If you draw your diagram here, we got mg, normal force, the tension to the right we get to ignore. We've got mg down here. That's the only force that is outside the system that's going to be causing the acceleration. The normal force and the weight on block A cancel out. So this is mg, our external force. The mass of our system will be the mass of the blocks added together. Since they're both mass m, that is just 2m times the acceleration. And you'll notice that both sides have an m. You can divide both sides by m and get rid of that. So g equals 2a. The acceleration is g over 2. Right? Which you could then, of course, calculate, but it says express all answers in terms of h, m, and g. Alright. Moving on to letter B. Block B strikes the floor and doesn't bounce. Determine the time it strikes the floor. Alright. So we've got a constant acceleration where a is g over 2. Anytime you've got a constant acceleration, you can use any of the kinematic equations that we learned earlier. So let's go ahead and look at that. We know that it's going to move a height h, right? We know that a is g over 2. We're looking for the time. We know that the initial velocity is 0. So I think we've got enough that we could solve. We've got our displacement. You call it delta y if you like, equals v naught t plus 1/2 a t squared. Right. Our first term is 0 because this is starting at rest. So our displacement, which is h, equals 1/2 times a, which is g over 2, times t squared. So if you rearrange this, I think you should get 4h over g equals t squared. So t would be the square root of all that mess. Square root of 4h over g, which the square root of 4 would be 2. So you could simplify this 2 times the square root of h over g. There you go. Moving on to part C, describe the motion of block A, so that's the one that's on the table, from the time t equals 0 to the time when block B strikes the floor. That's the time that we just solved for earlier. If you go back and look at your diagram here at the top, as B accelerates downward, A is going to move across to the right. They're connected by the string over the edge of the table, so if B falls a height h, A is just going to move across the table with height h. Since A and B are connected, they're going to accelerate together, which is what we said when we defined our system earlier. They're moving together, so we can call it one system. So we already know the answer to this one. Block A will accelerate at A equals g over 2 for t1 seconds, right? Where t1 is the value that they asked for this problem up here, right? T equals t1, where block B strikes the floor, right? Whatever that value is. And that's it. That's all you have to say. It's not doing anything else. It's moving to the right. I suppose you could say accelerate to the right in this diagram. The end. Okay. Don't say anything else, because that's all that's going on. All right. Then in D it says describe the motion of block A from the time B strikes the floor until the time that A leaves the table. Now, A will continue to move. In the problem at the top, here's some physics language here. It says that we're on a smooth tabletop. If they go out of their way to mention that it's smooth, that means that they're saying ignore friction. Friction is negligible. So block A will continue to move to the right, okay, but it won't be accelerating anymore, right? Because it won't have that external force from the weight of B to pull it down. So block A will continue to travel at a constant velocity from t equals t1 when B hits the ground until it leaves the table. Now it doesn't ask this, so I wouldn't say this in this question, but a follow-up question could be describe the motion of block A after it leaves the table. After it leaves the table, it'll be in free fall, and it would travel in a parabolic arc like we're going to talk about next unit. Alright, that's it for this problem. Hopefully it all makes sense. If you have any questions, feel free to ask tomorrow. Have a good night.